All right, so quadratic functions, 5.1.2, multiple representations of quadratic functions. And if you remember from past units in IM1, you've already explored multiple representations of a few other types of functions. So last year, you put some energy into your linear functions and exponential functions and trying to understand these four representations, which are a table that represents the function, an equation that represents the function, a graph that represents the function, and a situation that represents the function. And situation's pretty flexible. It could be anything from like a block pattern or number pattern to like, some actual real life situation, someone's walking down the street or whatever. So what we want to be able to do by the end of this unit is connect all four of these representations in both directions. So that means if we're given a situation, can we create a table, graph, and equation from it? If we're given a table, can we create a graph, equation, or even think of a situation that might fit? We want to be able to go back and forth between all of these different representations. So as we work, we're going to keep our mind on a few questions. What representations are we using? So which of these four things? What are the connections between them? Like which direction is our arrow going? Are we starting with an equation and ending with a table or vice versa? How can we use the representation to find more information? So that means like, can we see a pattern in the representation that could help us to get more details about the function? Or can we pull the key information out of our situation, that kind of thing. And then finally, what do we know about a parabola? And that means we want to like bring in our key features, which are all the things we worked on in the last lesson, like, our domain range, our vertex, our X and Y intercepts, is the graph opening upward or downward? There's all these different things that describe the graph and that can be relevant to our situation, to what we're working with. And each of those things shows up in these representations in their own way. So sometimes we're looking for a certain kind of number to determine a particular key feature of a graph, that kind of thing, of the function. All right, so today you're definitely going to need a calculator for the first problem we do. So go ahead and click the Desmos Scientific Calculator link for yourself there. And then I'm going to go to the next slide. So 5 seconds, click that link and have it off to the side somewhere for yourself. Okay. Okay, so our essential question today is, what key features of a parabola represent the launch and landing positions of a water balloon or any object thrown into the air and the maximum height it reaches? So just take a minute and think about if these people in this picture were to actually like pull that slingshot all the way to the ground and then let go. Imagine the path of the water balloon. Think about the launch point, the landing point, and where it might reach its highest point, like the highest height it can go. Remember, anything thrown through the air behaves like a parabola. So the water balloon would follow a parabolic path. So any thoughts on this, key features, things that we learned about yesterday in describing our graphs might be relevant here. So I'll give you a moment. All right, so technical difficulties. I don't know what happened with the slides not showing up. So anyway, back to this. So again, our learning objectives are to connect these four representations of quadratic functions. So interchangeably, graph, equation, table, situation, how do they connect, in what orders, that kind of thing. And here are those key questions we want to think about. And here's your Desmos Scientific Calculator link. So you go make sure you have that. Okay. And then your initial thoughts. So you should have had a moment to do that already because it did switch for you on the Pear Deck. So hopefully you're able to jot something down there. Okay. You have some great ideas here. So I'm seeing ideas about vertex. I'm seeing ideas about x-intercepts, y-intercepts. I'm seeing even like thinking about what angle it was released at, which could affect how far it goes or how high it goes, how much force behind the release. These are all really good questions. And some of them are more like a physics focused mathematics that would be relevant if we were wondering like how to maximize our height or our distance scientifically. And today we're just going to focus on the position of the water balloon. From where it starts, where does it reach its high point, and where does it land? But yeah, great ideas, everyone. There's some good instincts going on. And if you're feeling like unsure at this point, that's fine too. We're at the beginning of this process. It's okay to not know yet. All right, so here's a nice visual of a water balloon launch. So every year, Newtown High School holds a water balloon competition during halftime of their homecoming game. Each contestant uses a slingshot to launch a water balloon from the ground on the football field. This year, you are the judge. You must decide which contestants win the prizes for longest distance and highest launch. Fortunately, you have a computer that will collect data for each launch. The computer uses X to represent the horizontal distance in yards from the goal line and Y to represent the height in yards. So horizontal distance versus height. So this is a really important detail to just keep in mind as we go forward, that X is the horizontal distance in yards and Y is the height in yards. All right, so you can see how it launches into a curve that behaves like a parabola. All right. And there are 4 contestants in this contest. So we will do 4 different scenarios. I'm going to apologize now for the really cheesy names for each of the contestants. They're, you know, anyway, sigh. So contestant number 1, Magnanimous. The announcer shouts, Magnanimous, you're up first. She runs down and places her slingshot on the 3-yard line. After Maggie's launch, the computer reports that the balloon traveled along the parabola that represented by the quadratic equation y equals negative x squared plus 17x minus 42. Complete the table of values for the equation. So in order to do this, I want to make sure that we all have the tools we need to be really accurate with this. So what you want to do is make sure that you're using the inputs with the equation correctly. So you're going to want to plug your numbers in as carefully as possible. So I'm going to write out the equation with blanks for the x, and I'll add the square right there in just a second. Oops. And the reason I'm doing this is because I want to clarify something that can be a common error. Okay, so here's our equation without the x written. So it's a blank spot so that you could input the 3 inputs from the table. So when you input these numbers, what you want to do is, so say we input a 3 for x from the table. They're already giving us our inputs. We're going to put a 3 here. We're going to put a 3 here. And then we're going to work out what our y value is. This can be done all in one step in the calculator, but I want to encourage you to please use parentheses and be as consistent with mine as you can. Notice how the negative in the front is not inside the parentheses, it's outside the parentheses. That's a very important detail. in the original equation, the exponent, the squared exponent, only applies to the x, not to the negative. So when you punch this into your calculator, that negative is just out in front. So you're squaring the 3, but then it gets the negative after that, okay? So if we were to work this out sort of the long way, my next, like by hand, my next step would look like negative, then 3 squared, which is 9, then add 17 times 3, which is 51, then subtract 42. And if you're very careful with this, you should get that y is equal to 0. So your first entry in the table is 0. If you want to see that same thing on the calculator, here's how I would do it. I would start with my negative, right? We have a negative in front. So I put a negative, and then I'm going to use the parenthesis, then a 3, then close the parentheses. Then if you hit a squared, that will square your number. Then add 17, parentheses, 3, close the parentheses, then subtract 42. And you can see when you press enter, you can see I get 0. You can do it all in one line. Okay. Okay, so if you got 30.25 for the next point, good job. And then there's one last one. And if you got 0, you would be correct. So these are our data pieces from our table that we wanted to find. And then it's asking us at the bottom, what key features do each of the points represent? So I want to remind you of what X and Y represent here. So remember, the X represents like the horizontal distance, like the x-axis, right? So I'm going to just put a little note here. This is the horizontal distance. And then the y represents the vertical, like height, basically. Like the height vertically, or the vertical distance. So if we think about this, all right, so if the water balloon is at a horizontal distance from the end, from the 0 yard line, so it's at the 3 yard line. If it starts at the 3 yard line and its vertical height is 0, so it's hasn't gone anywhere yet, then this point would represent an x-intercept. So imagine like if you were to create a little visual to help. You don't have to do this, I'm just showing it so that you can see it. 3, 0 is like a point that intersects the x-axis. So 3, 0 might look like this. And 14, 0 might be way out here looking like this. And then 8.5, 30.25 is going to be somewhere out here. And our parabola is going to look something like this. So now if we think about it visually, the 3, 0 point, this point represents an x-intercept, and this point also represents an x-intercept, because that's where the height will, they'll be on the ground. They'll be on the horizontal axis on a graph. So we're going to go ahead and make a note of that. Okay, so I'm going to say 3, 0 and 14, 0 are x-intercepts. Okay. And then this other point, 8.5 comma 30.25, actually happens to be right smack in the middle of this parabola. Halfway between 3 and 14 is 8.5. It's exactly halfway. So that makes this the halfway mark. And remember, parabolas are always symmetrical, which means like this is the line of symmetry. This point right here is the vertex. So this point I'm circling in blue happens to be the vertex. So we're going to go ahead and make a note of that 8.5 comma 30.25 is the vertex. So just to keep in mind, when you're looking for x-intercepts, you're always looking for those points where y is equal to 0. That's a really important detail to be looking for, okay? And with the parabola, the vertex will be exactly halfway between the two x-intercepts. So the exact halfway mark between 3 and 14 happens to be at 8.5. And that's how we know that's precisely halfway and would represent the vertex. Okay. All right, contestant number 2. Generous. Generous. I know, it's horrible. All right, then you hear, generous, your turn, you're next. Jen runs down to the field, places her slingshot on the goal line, and releases the balloon. The computer reports the path of Jen's water balloon in the graph at right. Use the graph to fill in the table with the launch point, the maximum height, and the landing point. All right, so we're trying to look at the graph and identify the launch point, the maximum height, and the landing point. So just to give you a little direction here, we always are going from left to right. So she's launching from right here. All right, so I'm doing like the launch point in red. Okay, so put the launch point in your table. That's a pretty easy launch point to find. Okay, and then we've got the maximum way up at the top. That's the high point. So if you can find that coordinate pair, that's the next thing in the table. And then the landing point is back down here. Okay, so I'll give you a minute to fill in those 3 points. Resume recording. Okay, so here we go. We have our lowest bottom left-hand side point here, the launch point at 0, 0. And then we have the landing point on the other side at 8, 0. Oops. And halfway between them is our maximum height in the green spot, which is at 4, and then up to looks like 32. So this middle point will be 4, 32. And that's it. Okay. Next contestant. Contestant number 3, impeccable. All right, it's Impeccable's turn. The balloon launches. You hear a roar from the crowd. Turn around and splat. The balloon soaks you and your computer. You only have time to write down the following partial information about the balloon's path before your computer fizzles. Identify the launch point, the maximum point, and the landing point from this table. So we're looking for the launch point, the maximum point or height, and the landing point. Okay, so remember in the last couple slides that we were always looking for when the height is 0. And remember, we have our horizontal distance is x, but our vertical distance is y, like the y-axis is vertical. So if the height is 0, y is 0. So what that tells me right away is that this right here is the launch point. It's the x-intercept. So we can go ahead and make a note of that ordered pair. So this is our this is our first point, 2, 0. That's our launch. Now we're looking for the maximum. So where is the highest point? Where is it highest? Where's our vertical height the most? So take a look around. Can you find the point that has the highest measurement vertically? And I see a few people finding it, and that's great. And yes, so a handful of people have found it, and they are all correct pretty much. So if you got that the highest point is at 7,25, you're correct, because 25 is definitely the highest number that this thing is reaching. Do you see that? So this is our maximum. We're going to put this at 7,25. Oh, don't forget your parentheses. All right, so there's our maximum. And now we're kind of in a pickle. We have our launch point, we have our maximum, but remember the landing point is on the ground as well. So we don't have like the matching point on the other end. We don't have the final landing point. What we do have though is number patterns. So what I'm going to do is I'm going to extend my number patterns out a couple of places. So do you see how in the X's, it's counting by ones, 2, 3, 4, 5, 6, 7, 8, 9. So the next one would be 10, and then 11, and then 12. And hopefully that's enough for us. And then if we want to find the number pattern for the Y's, take a look at what we have here. We have our highest point here at 25, but notice how 24 and 24 on either side, those match. 21 and 21 on either side of that, those match. So the next one, 16 and, oh look, 16. The next one should be 16. And then if we follow that same pattern, the next one should be 9. And finally, the last one here that we have should be 0. And now we have the landing point, because we're always looking for a 0 in the y coordinate. And there it is. So I'm going to go ahead and type that in, that our landing point is at 12, 0. All right, contestant number 4. Altruistic. Another special name. Okay, finally, the announcer calls for the last contestant, altruistic. With your computer broken, you decide to record the balloon's height and distance by hand. Al releases the balloon from the 10-yard line, and it lands at the 16-yard line. Based on your previous launches, you estimate Al's balloon reaches a height of 27 yards. All right, so I'm going to go ahead and just underline those key things. We have a 10-yard line. It's released from the 10-yard line. We have it lands at the 16-yard line, and it's got a maximum height of 27 yards. Sketch the graph of the pathway and to help you determine the launch point, maximum height, and landing point. And then add them to the table. Okay, so this is what we're trying to find for the table. Our launch point, our maximum height, and our landing point. All right, so we need to sketch the graph. So remember that 0, 0 is sort of like at the 0 yards line, you know, at the end zone, basically. And it says that it's launched from the 10-yard line. So we actually have to travel out a little bit. So we're going to go out about 10 yards. And because it's a sketch, we really don't care how perfect this is. We just need to know that it's 10. So I'm just going to put a 10 on it because that, you know, helps me organize my work. And then it's going to land at the 16-yard line. So, you know, a little ways further, 16, it'll be back on the ground. And then it's going to go up in the air and come back down right there. So there's our water balloon launch. And it says that the maximum height is 27 feet. So remember, X is the horizontal distance, but Y represents the vertical distance, the height. So I'm going to put a 27 here on the Y-axis. All right. So when we're identifying now our key points on our table, we have partial information here. We have x-intercepts that have a x value of 10, like there's our launch value, and an x value of our landing at 16. We have a maximum height of y is 27, so I'm going to go ahead and put a 27 here. And now what we want to do is figure out what are the other parts of these coordinates. So I want you to take a minute and see if you can complete the ordered pairs in the table that I've started. All right, so we're going to fill in the rest. So when we're on the x-axis, a point right on the x-axis, x is the number, and then y will always be 0. When we launch a water balloon from the ground, the height is 0 because it's on the ground. And then when it lands, the height is once again 0. So these 2 points, 10 and 16, represent the x-coordinate of our x-intercepts, but 10, 0, 16, 0. There we go. And then our middle point, our highest point, our vertex, is going to have to be, because of the nature of a parabola being symmetrical, it's going to have to be exactly halfway. So what we have here is an ordered pair. Where the y is 27 and we're trying to find the x. So we need a point that's halfway between 10 and 16, and exactly halfway between 10 and 16 is 13. So in your table, you can finish it up with 13. Yay. Okay, I'm going to go ahead and clear it. We need to move forward. All right, so what we need to do now is compare all of their different launches. So we're going to just do real quick, we're going to graph these things and determine who had the longest distance and who had the highest launch. And I'm going to do this in different colors. That's okay. All right, so I'm going to go ahead and pick some colors. So let's say Maggie's in pink. So go ahead and graph in pink for Maggie. All right, so we're going to go 3, 0 and 14, 0. Notice how that's 11 units apart. 3 to 14 is 11. So like the distance for her is 11 yards. That's how far hers went. And then her height or highest point is 8.5 comma 30.25. So just above that line. And when you make your parabola, it's probably going to look kind of funky. Try to make it as smooth as you can. Sometimes it works best to start from the vertex. There's Maggie's graph. All right, now I'm going for Jen. Jen in blue. Okay, 0, 0. Now to 8, 0. So from 0 to 8, her horizontal distance is just 8 yards. Let's see, 432 in the middle, 4. But she did actually beat out Maggie for height at 432. Okay. All right, imp. Here's imp in green. So let's see, at 2, 0 now to 12, 0. That's a distance of 10 yards. So this distance is 10 yards and a height of 25 at 7. All right, so see, 25 is definitely not as tall as either of those first two. And then Al. Okay, so we have 10, 0 as a starting point now, and 16, 0. So that's only 6 apart. Do you see how far apart those are? 6 apart from the two x-intercepts. The height of 27, so 1327. Okay. All right, so I know your graphs are probably looking a little funky, and that's okay. Make sure that they're not too pointy in general when you do a parabola. No need to change it right now, but I just just remember that this is a water balloon launch, so those things aren't going to zigzag their way up into the air. They're not going to go like up and straight down. They're going to do a rounded curve. They're going to arch. So just keep that in mind in the future when you're graphing your parabolas. Okay, that they'll look less like triangles and more like curved mountains or whatever. All right, so when we decide who's the winner here, I already did some of the work for the longest distance. Do you see how the distance between the launch and landing points for Maggie is 11, and that's bigger than any of the other distance from launch point to landing point. So that means that Maggie is the winner of the longest distance with her 11 yards. Okay. For our highest launch, though, we're looking for something different. So this time we're looking to compare the height. How high up did they get? And it looks like this blue one made it up higher than any others. And if we double check the vertex and the y coordinate of the vertex, you can see 32 is bigger than all the other y coordinates. So here's 32 is the winner. There's a bunch of stars for 32. All right, so that means Jen is the winner of the highest launch. And 32 yards is like 90 something feet. That's very, very high. All right. So we're getting short on time, so I do want to make sure that we are able to finish. There's only one last question and then your closure. All right. I'm going to go ahead and clear mine. All right, so on our last slide here of the lesson, we're just clarifying that the features that represent the x-intercepts and the vertex in the context of the water balloon launch, the x-intercepts represent the launch point and the landing point. The launch point and the landing point are the x-intercepts. The vertex always represents the maximum height. Okay. All right, so your summary is essentially to rehash this again in your own words. And here it is. Okay, so we always want to revisit the essential question and make sure that we get it now.